Good afternoon. In the last class, we have discussed about the rolling process, concept of rolling process, different types of rolling mills with the special rolling mills, uh, uh, microstructural and metallurgical, mechanical properties, how they are changing under a rolling process onto the what sheet metal. All we have discussed in the earlier class. Then now we will discuss about the what relations used to solve the numerical problems. What exactly the rolling load, rolling force, and other parameters required, power, torque, other parameters required for solving other problems. We'll discuss them. So you look at the picture, consider rolling operation of sheet, let the compression be under plane strain condition, that is two-dimensional state of stress then. So let H naught be the thickness of the sheet at the entrance and V naught is the velocity of the strip at the entrance. H1 is the thickness of the sheet at the exit and V1 is the velocity of the sheet at the exit and B is the width of the sheet and R is the radius of the rolls. The volume of metal entering the rolls must be equal to the volume of metal leaving the rolls. In plane strain, the width remains unchanged and hence according to the volume constancy concept, initial volume equal to final volume. Therefore, B is constant, width is constant in rolling process. Therefore, H naught V naught is equal to B into H1 N1. So, by equating these and simplifying, V1 H1 V1 by H V1 by V naught is equal to H naught by H1. To satisfy the above equation, the exit velocity V1 must be greater than the entrance velocity V naught. Thus, the velocity of the strip from entry to exit must be increasing gradually. However, some of the what important terms related to the what rolling process with respect to the to solve numerical problems and what angles and different terms required and their relations are discussed with respect to the figure. Maximum angle of bite or angle of nip, then no slip angle beta, that is maximum angle of bite or angle of nip alpha, then no slip angle beta, neutral point, lagging zone, forward slip zone, radial and tangential forces, roll separating force, specific roll pressure, draft, are and some other terms are required to but derive an equation. So maximum angle of bite or angle of nip alpha then. So the maximum angle for which metal piece will enter rolls without pushing is termed the maximum angle of bite or angle of nip then. When smooth rolls, the maximum angle of bite at which the hot metal will enter the rolls is about 30 degree. When the rolls are roughened, then the maximum angle of bite may be around 40 degree. However, from the figure we can see that when the strip enters the roll gap, it results in a normal force P and a frictional force F. The horizontal component of the normal force is PR is equal PRH is equal to PR into sine alpha, and the horizontal component of the frictional force F suffix H is equal to F cos alpha. So now the strip to enter the roll gap, the horizontal component of the friction force must be equal or greater than the horizontal component of the normal force. Thus the thus the minimum condition for the strip to enter into the roll is Fh is always greater than or equal to the PRH, that is the frictional force is equal to or greater than the normal force. Therefore, from the above relation, F cos alpha is equal to P sin alpha. F by PR is equal to sin alpha by cos alpha, that is equal to tan alpha, means sin by cos is equal to tan alpha. Since F is equal to mu into PR, then therefore by simplifying, mu is equal to F by PR. So therefore mu is equal to tan alpha, you call it as equation 5.2. Therefore initial volume equal final volume, that is V naught by V1 is equal to H naught by H1, you called already equation 1. Then mu is equal to tan alpha, it is equation 2 then. Thus for a workpiece to enter into the roll gap, the coefficient of friction should be equal or greater than the tangent force of the angle of the contact angle or angle of bite. Then coming to the second angle, that is a no slip angle, it is denoted as a beta and clearly mentioned in a figure. Then the angle between the neutral point and the lines of the rolls is termed as no slip angle. Look at this, the angle between the neutral point and the center lines of the rolls, it is termed as no slip angle. Then coming to the neutral point, as the velocity increases steadily from entry to exit, at only one point in the roll gap, the surface velocity of the roll will be equal to the forward velocity of the metal. The point is termed as neutral point, or the corresponding section it is exactly termed as a point of no slip. This section it is termed as neutral section. The velocity of the metal as it enters at x will be less than the velocity of the rolls. It is gradually increases and reaches the roll velocity at the neutral point n, and then onwards it will be more than that of the rolls and reaches the highest value at y. Then as it leaves the roll, then this means that at all the sections except the neutral section, slip must be takes place between the metal and the rolls, clearly shown all these sections in the beginning figure. Then coming to the lagging zone, then between the entrance plane and the neutral section, the sheet is moving slower than the roll surface, causing slip, and the frictional force acts towards the exit and draws the metal into the rolls. This zone where sheet metal moves slower is termed as lagging zone. So then coming to the forward slip zone, on the exit side of the neutral section, the sheet metal faster than the roll surface, causing the slip, and the frictional force act toward the entrance and oppose the delivery of the sheet from the rolls. This zone where metal moves forward and faster than the roll is exactly termed as a forward slip zone. Then coming to the radial and tangential force, at any point along the surface between the roll and the metal, two forces acting on the metal. These forces, these are the what radial force P and the tangential force F. The radial force acts at any point along the surface of contact and passes through all the roll center and act always normal to the tangential force. The tangential force is tangential to the roll surface and is normal to the radial force. It is all shown in the what picture. Then you go through the picture and identify the what all these angle, surfaces and points where exactly maximum load force acted over the sheet. Then roll separating force. The radial force PR is a rolling load also, causing metal deformation. This what force is always equal to the reaction created to the metal surface that is trying to force the roll apart. It is also termed the roll separating force. Specific roll pressure. The rolling load applied per unit area of contact between the rolls and the metal, it is exactly termed as a specific roll pressure. The area of contact is given by the product of the width of the sheet W and the projected length of the arc of contact LP. So therefore the projected length of arc of contact is given by LP is equal to R into H naught into R into H naught minus H1 minus H naught minus H1 by 4 to the power of 2, half. Then therefore R into H naught minus H1 to the power of half, that is equal to square root of R into delta H. You call it as equation 5.3. Thus the specific roll pressure P specific is equal to P by B into LP, where P is the rolling force, B is the width of the sheet, and LP is the projected length of arc of contact. So then in the equation 5.3 we have used a delta H, that is a draft. Then in rolling process, draft it is defined as the difference between the initial and the final thickness of the product. That is draft is equal to delta H, denoted by delta H, that is equal to H naught minus H1 Therefore, draft is a function of the coefficient of friction and the roll radius. From the equation, we have length of arc of contact LP is equal to square root of R into H then. R into H then. It is given in the equation then. Therefore, tan alpha is equal to square root of delta H by R, that is by after expansion and neglecting some terms, and we will get a equation then. But from equation 5.2 we have then mu is equal to tan alpha, that is equal to square root of delta H by R then. So therefore the maximum of delta H maximum is equal to mu square R then. So that is, you call it as equation 5.5. Therefore from this equation we conclude that higher the roll radius, higher the friction, greater the draft, which means higher reductions are possible for a given friction condition. A higher roll dia can be bite a thicker billet than a small dia roll. So therefore mu plays a vital role in the equation then. Coming to the rolling load then, from the slab analysis for plane strain condition, the maximum pressure between the work and the tool, it is given by P max is equal to 2 into K into exponential mu B by H. That is what plane strain flow stress, nothing but what K. You call it as a equation 5.6a. The mean pressure P bar average is equal to 2K into H by mu B into exponential mu B minus H then. That is called it as equation 5.6b. In rolling, if the roll curvature is neglected, the process can be considered being under the plane strain compression. Thus for sliding friction, equation 5.3, that is what a projected length of arc of contact, is applicable for the variation of the rolling pressure, while equation 5.4 holds good for the mean pressure. The term B in these equation means equation 5.4, that is the specific roll pressure. The term B in these equations should be replaced by the equivalent term LP, that is roll contact length, and H the average height of metal between the roll gap. Therefore H bar is equal to H naught minus H1 by 2. Hence mean roll pressure is given by P bar average is equal to H by mu into LP into exponential mu LP by H minus 1 into sigma naught. You call it as equation 5.6c. Here sigma naught is the average plane flow stress, that is 2K, across the roll gap. If the metal is assumed to undergo work hardening, for a simple approximation of sigma naught, therefore sigma naught is a sigma 1 plus sigma 2 by 2, where sigma 1 and sigma 2 are the flow stresses at the entry and exit of the roll. Equation 5.6 can be rewritten as P average is equal to sigma naught into 1 by Q into e power Q minus 1. You call it as equation 5.6d then. So where Q is the factor then, therefore Q is equal to mu LP by H bar then. The average rolling force is given by multiplying the roll area under pressure then. Therefore B into LP, that is B into LP, you substitute that value in the equation. Therefore P average is equal to sigma naught into 1 by Q into EQ minus 1 into B by LP. You call it as equation 5.7 then. So in rolling force, the friction adds power loss and hence higher rolling load, but it is an important factor in pulling a slab into the roll gap. Therefore the frictional contribution to the rolling force is in the factor Q. Though the friction varies from start to end along the arc of contact, it is difficult to measure the varying friction under roll. For all calculations, a constant value of friction is taken into account. For cold rolling, the value of mu is in the range of 0.05 to 0.1. For hot rolling, the friction value is higher and it ranges from 0.2 to 0.4, and sometimes stiction friction also exist. Under sticking friction conditions, the friction factor is 1 then. Therefore, the rolling load with the sticking friction can be calculated by using the equation P average is equal to sigma naught into LP by 4 H bar plus 1 into BLP. We call it as equation 5.8, that is used to find out the average rolling pressure. Then coming to the what friction hill and the distribution of roll pressure. The distribution of roll pressure along the length of contact between the roll and the work is not uniform. It increases gradually from entry point, becomes the highest at the neutral point, and reduces gradually towards the exit. The pressure distribution along the projected length of arc is given in equation given in figure 5.2. Therefore, the pressure at the entry, at the neutral point, and at the exit varies. Therefore, this what ultimately produces a waviness on the what part produced. Then, therefore, by what flatting the what theoretical and experimental values, then so we can conclude that the frictional hill flatted based on the theoretical calculation rises to a sharp peak. However, then experimental pressure distribution is a smooth curved peak around the what neutral section. This clearly indicates that neutral point is not actually a line contact, but it is an area due to roll deformation and other variables. The shaded area above AB in the curve indicate the force required to overcome the friction between the work and the rolls, while the area below AB indicate the force required for homogeneous deformation of the metal in plane strain condition. However, then so all it will be taken into account while you were what calculating the thickness of the metal, exact value of the what thickness to be reduced between the two rolls. Then how to calculate the torque and power? Then the torque required to rotate the roll is calculated by assuming the rolling force P act at a point along the arc of contact at a distance A from the center of the rolls given in the figure. Then to calculate the momentum arc, it is usual practice to consider ratio of momentum arc A to the ratio of the projected length of arc, that it is given in the equation lambda is equal to A by R into H naught minus H1 to the power of half, where lambda is the 0.5 for hot rolling and 0.45 for cold rolling. The torque is the product of the total rolling load and the effective momentum arc. Since there are two work rolls to be driven, then the torque will be T is equal to 2PA. It is clearly given in the figure then, because all total torque is equal to 2 times of P into A, given in the equation and shown in the figure. Therefore, the work done is equivalent to the distance moved by the resultant rolling load P. Since the distance moved is equal to 2 pi A, and for two working rolls, the work done is given by work is equal to 2 into 2 pi A into P. They call it as equation 5.12. Since the power is the rate of doing work, the power required to run pair of rolls revolving at n revolutions per second is given by WR is equal to 4 pi APN by considering speed, the feed of the roller and periphery of the roller. Power can be calculated by using this equation. Total work done can be calculated by using this. Then how to determine the power loss due to friction in bearings? So because of heavy loads, there exists a high friction in the bearing supporting the rolls. This leads to a considerable power loss. The analysis to estimate the exact power loss in the bearing is complicated. Hence, estimation of the power loss due to friction in bearing is given by the empirical relation WB is equal to half mu B FB dB into omega, where WB is the power loss in the bearing due to friction, mu B is the coefficient of friction in the bearing, it is between 0.002 to 0.01, and Fv is the radial load on each bearing, that is F by 2 when each roll is supported by two bearing. F is equal to rolling force or roll separating force. dB is the effective dia of the bearing. Omega is the angular speed of the bearing. Therefore, for roll supported with two bearings is the total power loss WL is mu b FB dB W. Therefore, the total power required, that is given in equation 5.4 then. Therefore, the total power required of a rolling mill Wt is equal to Wr plus Wl. That is the work done plus work loss. That is what total power required given in equation 5.2. So these all will be taken into account while solving numerical problems with respect to what various parameters used for calculation of various parameters of rolling process then. So thank you then. We'll solve the what numerical problems in the next class, next video class. Thank you.